A very warm welcome to the demo lecture. So in this lecture, we shall introduce the topic of signals and systems. The topic of signals and systems is very vital in the field of electronics. If you look at any electronic circuit, signals as well as its interaction with systems, which is the circuit itself, is very common. In this, we shall analyze the definitions of signals as well as systems. So let us see what does it mean by a signal. So a signal is any function defined on an independent set of variables. Now let us see a few examples of a signal so that it is made clear. Now let us pick up the first keyword of this definition, which is a function. So all of you are familiar with what a function in mathematics mean. So function is a entity which takes in some independent variable as its input, and it gives out a value corresponding to that particular independent variable. The simplest example that we can choose from the field of the electrical engineering point of view is a voltage signal or a current signal. So the voltage signal is represented as V of t and the current signal is represented as I of t. The function of interest in this case is V and I, which represents the current or the voltage. And the independent variable here is the time t. It is called independent because it does not take any value which is dependent on the function as it is, whereas it takes the value to be any particular point in the real line or in the positive real line. So in that case we call t is an independent variable. So I use a shorthand here for independent. Okay. Now, can we have more number of independent variables? That is a question that we can ask. So we consider the second example of a signal, which is an image. How do we represent an image? So image is a picture. So let us draw an image. So the image is encapsulated inside this rectangular box. There is some object in this image. And a digital image, for instance, is comprised of a certain number of columns and a certain number of rows. So we represent it by the grid representation. Now, each of these rectangular boxes represents a picture element or a pixel. So there are some n number of rows and there are some m number of columns that will form the picture. So let us just write down that some n number of rows and m number of columns. So it is an n cross m image. Now how do I represent each intensity of the pixel? So the intensity of each pixel can be written as I of xy. So xy denotes the spatial location of each of the pixel, and I of xy represents the intensity function or the intensity of that particular pixel. It is a representative of the intensity of the color of the pixel. So we shall not see this into much detail now. So we have understood what is meant by a signal. Let us consider the second term in our topic, which is system. So system can be defined as an entity in the form of an entity or a block. This is the common term that we use in the language of signals and system. We use system as a block. So let us call it as an entity. So an entity which takes sorry which takes an input function and transforms, let's say use this word, transforms it into an output function. We can now represent a system using the following block diagram. So let us see the block diagram which represents the system. So for the time being, we call the system using its shorthand S bar M. We have input to the system which is represented by say x of t, and we have an output to the system which is called as y of t. So for the purpose of explanation of a system, we usually define systems using the simplest set of functions, which is a function in one variable. So here the functions that we choose are functions of time, as we um, uh, told earlier that we will be commonly dealing with functions like voltages or current that are common in electrical electronics engineering. So here we are defining the system block diagram using the functions x of t and y of t. So with that understanding of the block diagram, we shall move into the different classifications of systems. So we first introduce the notion of a linear system. What is meant by a linear system? So the term linear arises from the notion of a line. Now, we will note that the linear system is not quite a line, or not quite compliant with the definition of a line, whereas it is quite a bit like vector spaces in vector algebra. So let us see how we can define the linear system using the help of a few examples. So we take up these examples. The first example that we take is that of an amplifier system. Amplifier. What does an amplifier system mean? So the amplifier system can be represented as y of t equal to some c times x of t. The direct system, its output y of t is some scaled version of the input x of t. Now, we have to check if the system satisfies the linearity definition. The definition of linearity can be represented in the form of the block diagram itself. So let us take the block diagram once again and explain the definition. So we have the system, and let me just denote a set of dashed lines. So let us consider two inputs, x1 of t and x2 of t, and their corresponding outputs, y1 of t and y2 of t. The definition of linearity of the system says that if I add the two inputs and feed it into the system, I should get the corresponding sum of the outputs, which is y1 plus y2 of t. Or in other words, we can say that the output corresponding to the sum of the input is the sum of the individual outputs. One can easily verify that the amplifier system that we have written down here satisfies this relation. Now, is that it for the definition of linearity? No. We require one more aspect to define the linearity of the system, which is termed as the homogeneity property. Homogeneity property. So what is homogeneity? It says that it is somewhat related to the amplifier system that we had considered. So in the system block diagram, we have an input. This time we call it as just x of t, and the corresponding output is y of t. Now on feeding some alpha scaling factor of the previous input x of t, that means I am going to feed alpha times x of t into the system, then the system would output some alpha times y of t, the same alpha, which is non-zero. For the time being, let us define alpha to be non-zero. It outputs the same alpha times the output. Now one can also verify this for the amplifier system. So the amplifier system is linear. Now let us take a negative example to understand this property more clearly. So the second example that we consider is that of a squiring system. A squiring system. As the name suggests, the system can be represented as y of t is x of t square. Okay, so to check the linearity, we have to do the following. If I give x1 of t to the system, so let me just represent it using this, it would give y1 of t. Okay. Similarly, if I give x2 of t to the system, another input, it would result in y2 of t. Now from the system definition, I can get rid of this y1 and y2 and just write it as x1 squared t, x2 squared t. Okay. Now I do the following. We can perform the summation operation x1 plus x2. I'm going to add pointwise the signal x1 plus x2 of t, and if I pass it through the summation system, it would result in, say, x1 squared plus 2 times x1 x2 plus x2 squared of t, which is not equal to the individual or the sum of the individual outputs, which is equal to x1 squared plus x2 squared of t. So this is a negative example, or this is a system that is non-linear. This is a non-linear system. It's a non-linear system. Now let us come back to the definition of linearity once again. We define linearity to be composed of additivity and homogeneity. And we defined that the term linear is derived from its base word line. So let us take the equation of a line here. The line. So this is our third example. We are going to make a system look like a line. So we know that the equation of a line is y equal to some ax plus b. So I have left a few gaps due to some reason, because I can extend it to the definition of a signal now, which is a function of t, right? So a and b are just constants which represents the slope and the intercept. Sometimes this equation can also be written as y equal to some mx plus b. That is also equivalent. Now we have to check if this is linear or not. So let us just directly write y1. So I'll use a quite different notation here. I'll just write y1 comma 2, which implies that I'll be taking only one of the index at a time. So I can write y1 comma 2 of t is a x1 comma 2 t plus b. So you should read this as two equations. The first equation is y1 t equal to a x1 t plus b, y2 t equal to a x2 t plus b. So this is the shorthand representation of the two equations. So this implies that if I add the sum of y1 plus y2 from these two equations, I should get it as a times x1 plus x2 of t plus 2b. Note the fact it's 2b here, which is not the output corresponding to the sum of the inputs. So the output corresponding to the sum of the inputs would have been like replacing this xt by x1 plus x2t. So that is the difference that we get. So this system is also not linear. Even though it has the definition of a line, it is, let me put it here, it is not linear. It is not a linear system. Now we shall go into some other classes of signals as well as systems. Now we have learned a class of systems which are known as the linear systems. So let us consider this class of signals now, which is a continuous time signal. What is meant by a continuous time signal? In short, sometimes this might be represented as CT, continuous time. So take any arbitrary signal. This is time, this is amplitude, let us write it as v of t. A continuous time signal has two characteristic properties. One is that it has continuous amplitude. It is continuous in amplitude, and the second is that it is continuous in the time axis also. Alright. Now the opposite class or the second class of signals that we can consider is what is called as the discrete class or discrete time signal. So by discrete time signal we mean that we have discretized the time axis of the continuous signal. So let us just see the discretization process that it undergoes to make this idea very clear. So we have the block which is called as a sampler, which is vital in the discretization process with respect to time, and one of its input is what is called as the sampling time or the sampling interval. Sampling interval. The input to this is our continuous time signal x of t, and the output is x of n times the capital T, or sometimes this is equivalently represented as just x of n within square brackets. So with that brief introduction into the definitions of signals and system and the different classes of signals and systems that we can have, we'll end the demo lecture here. Thank you for listening.